WebAssign Week 9, Problem 6. So we've had a bunch of different problems on induction this week, and in most of those problems, you had a loop and a magnetic field that was changing, and that's related to current flowing in the loop. And this problem is similar to those, but it's backwards. In this case, we aren't told what the magnetic field is and how it's changing and asked to figure out what the current is. No, instead, we're told what the current is, and we have to work back and figure out how the field must be changing. So what we're trying to do is get the function that describes the B field and how it's changing with time. So that's what we're seeking. What we're told is that the current is varying according to this formula BT squared, where B is some constant. Remember, all of this is based on Faraday's law that the EMF induced in a loop like this is equal to the rate of change of the flux. The flux, phi, being B perpendicular times the area. We'll just say B times area. The field is supposed to be perpendicular all the time. It's uniform everywhere. It's changing with time, but not with space. So we can just use B times A for the flux. And in this case, that would be this, this particular function that we don't know times the area of the loop. Now, what we're told is current, but what I'm talking about here is EMF. How are those two related? Current will flow around here. Well, the EMF is sort of like the battery that drives the current around, but the other factor in here is the resistance of the wire. And so the EMF, which is like the battery or the voltage, and the current and the resistance are all related in just the usual expected way, that the EMF is equal to I times R. This is voltage is equal to current times resistance. That's just Ohm's law. So one could keep going with this and now just say that I times R, we could substitute in what I is as well here, but I times R, and there's a minus sign in here as well I didn't bother with, d by dt of phi. Phi is B times A. The minus sign really doesn't matter. Nothing in the problem tells you how we're measuring current, which way are we connecting a meter or whatever, nor is there any description of even which direction is the magnetic field going. None of that is provided, and so this minus sign is sort of irrelevant. You could obviously get either answer, so we're going to ignore it in just a moment here. So putting in what we have, the current we know is B times T squared times R, and that equals, and now I'll drop the minus sign, d by dt of this function B times A. So we've got a derivative of time derivative of this function B is equal to some stuff over here that involves time. Could move A over here and make it a little bit clearer. Let's rewrite it as B. I'm going to put together R and A, all the constants, and then we have T squared, and that equals the derivative of this function we're trying to find. So now we have the time derivative, the derivative with respect to time of this function we'd like to know, is equal to this. Well, if the derivative is known to be that, then how do we get this thing? How do we get B if we know what its derivative is? We have to invert the derivative. We have to integrate. So take the integral of both sides. And what you'd have on this side is B R over A T squared dt is equal to, and over here it'd be the integral of db of t. This just turns into b of t. There's also a constant of integration here, but they tell us that in the problem that b of t starts at 0 when I starts at 0. So that constant will turn out to be 0 as well. You wonder, how did I get from this line to this line? One way of thinking about it is I sort of split up the pieces of the derivative. It's not really what you're doing, but that kind of works. So you move the dt over here. So you're taking an integral with respect to time, and here you're taking an integral of these little pieces of bt, and you just get the whole bt that way, b of t. Okay, so to carry out the integral now, we're trying to see, well, what is b of t equal to? Look at this integral, and you should realize we can simplify this. Some of these things are constants. R, that's the resistance of the loop, that's a constant. The area of the loop is a constant. Even this factor little b is also a constant. We can move that outside of the integral. So we have br over a times the integral of t squared dt. And now you should all remember your calculus and see if you can integrate that, the integral of t squared dt. What's that going to be? Well, 1/3 t cubed. And so that's our function. That's the answer.